introduce our group members. Firstly, my name is Muhammad Zimilki. Secondly, Muhammad Shahid Hamid Muhammad Kifli. Thirdly, Muhammad Irfan bin Mas'ad. And lastly, our group member is Muhammad Afnan bin Akmi. So, let's go to the introduction. Newton's law of cooling states that the rate of cooling of an object is proportional to the temperature difference between the object and its surroundings, provided that this difference is not too large. If we let T be the temperature of the object at time T and Ts be the temperature of the surrounding, then we can formulate Newton's law of cooling as a differential equation below, as you can see at the slide. So let's go to the problem statement 1. A glass of hot water has an initial temperature 80 degrees Celsius. Placed in a room where the temperature is 30 degrees Celsius. After 1 minute, the water temperature dropped to 70 degrees Celsius. What will be the temperature after 3 minutes? And at what time the water cool down to 40 degrees Celsius?
Okay, the solution for the problem statement 1. For this question, the initial condition or initial temperature of the water is 80 degrees Celsius and the temperature of the room is 30 degrees Celsius. Next, additional condition or the temperature of the water for the first minute is 70 degrees Celsius. Next, we need to find C. So to find C, we need to apply general equation of the Newton's law of cooling, which is T equal to Ts plus Ce to the power of Kt. Okay. So next, we need to substitute the value to the equation. T0 equal to 30 plus Ce to the power of 0. Since anything that to the power of 0 equal to 1, so we got 80 equal to 30 plus C, and so the answer for C is 50. Okay, next, to answer the question of problem statement 1, find additional constant K. Okay, so the equation is 30 plus 50 to the power of Kt. 50 is C that we calculated before. So T1 equal to 70 degrees Celsius, which is the temperature of the water for the first minute. So 70 equal to 30 plus 50 to the power of K. So, and the answer we got for K is ln 0.8. Okay, next, to find to answer the question of problem statement 1, which is to find the temperature of the water after 3 minutes. The equation to find this is T equal to 30 plus 50 to the power of ln 0.8 T. Okay, so we substitute T for 3 since we need to find the temperature after 3 minutes. T3 equal to 30 plus 50 to the power of 3 ln 0.8. And so the answer we got, the temperature of the water after 3 minutes is 50.6 degrees Celsius. Okay, the next question, what time the water cools down to 40 degrees Celsius? For this question, the equation is T equal to 30 plus 50 to the power of 30. We substitute T to 40 since we need to find the times when the water cools down to 40. So we substitute the T for 40. Okay, after we solve the equation, the answer, the conclusion that we got is T, the times when the water cools down to 40 is 7.2 minutes or 7 minutes and 12 seconds.
Okay, now we go for problem statement 2. A bottle of soda at room temperature 72 degrees Fahrenheit is placed in a refrigerator where the temperature is 44 degrees Fahrenheit. After half an hour, the soda has cooled to 61 degrees Fahrenheit. For A, what is the temperature of the soda after another half hour? And for question B, how long does it take for the soda to cool to 50 °F? Okay, let's go for calculation and solution for these problems. In this question, the initial condition given is T0 equal to 72 degree. For temperature is Ts equal to 44 degree, and for additional condition given is T30 equal to 61. Next, we need to find C. First, we need to use the general equation from Newton's law of cooling, which is T equal to Ts plus Ce kT, where T is the temperature at time T, Ts is the surrounding temperature where Ts equal to 44 degree, then C and K are constants to be determined. Second, we need to substitute the initial condition T0 equal to 72 into the equation. So we get 72 equal to 44 plus CEK0. Since EK0 equal to 1, the equation simplifies to 72 equal to 44 plus C. And then we can solve for C, thus the value of C is 28.
So this is a solution for the problem statement number 2. First, we need to put the information that we got into the equation. So as you can see, T equal to 44 plus 28 E power of KT. 44 is the temperature in the refrigerator, while 28 is the C that we calculate for. So we need to find K in the solution that we got. This is the additional condition that provided in the statement. E30, which is 30 minutes that the soda cooled to 61 degree. So we can put the information that we got into the solution. We got 61 equal to 44 plus 28 E the power of 30K. So K equal to minus 0.0166. The new equation that we got is T equal to 44 plus 28 E the power of minus 0.0166. So let's answer question A. What is the temperature of the soda after another half hour? So we need to let T equal to 60. Because another half hour means it's 1 hour. Then we can put T to the solution. So we got T 60, 44 plus 28 E power of 60 times minus 0.0166. The final answer is T 60 equal to 54 Joule. Next, for the question B, how long does it take for the soda to cool off to 50 degree Fahrenheit? First, we need to let the equation that we got equal to 50. So T equal 50, and the equation that we got is 50 equal 44 plus 28e the power of negative 0.0166t, and for the final answer, T equal to 92.9 minutes. Thus, the soda needs 1 hour 33 minutes to push to 50 degrees Fahrenheit. By completing this case study, we have learned that first-order differential equations are used in real life to solve many problems, including cooling and warming problems. We can conclude from the equation the problem statement in this case study that by using the application of Newton's law of cooling, we can compute the expression for time needed for the soda to cool 80 degree Fahrenheit in the given room temperature of 44 degree Fahrenheit approximately 1 hour and 33 minutes. And for the problem statement number 2, the hot water cooled from 80 degrees Celsius 4 degrees Celsius in a surrounding temperature 30 degrees Celsius 7 minutes. Throughout the calculations, we determine the constant K based on the given conditions such as the initial and intermediate temperatures. We validated that the exponential decay model ET equal to Ts plus Ce the power of K fits accurately for predicting cooling times and temperatures at specific moments. This case study highlights how differential equations offer practical solutions to temperature management in diverse situations, from beverages to environmental heat exchangers.